implementation of GPT-3 175 billion parameters that we have available in our examples on GitHub. So in terms of GNNs, the architecture of the IPU is well suited for the fine-grained operations because of the MIMD paradigm that is implemented on the chip and the large memory bandwidth that we have. And we have a lot of parallelism and connectivity within the POD64 that is available in ALCF at Argonne. Some data points regarding GNN would be the competition that Stanford organizes, the Open Graph benchmark large-scale competition that was published at NeurIPS last year, and GraphCore team in partnership with Mila and Valence took 2 first places out of 3, which was a very exciting achievement for us because many large companies were also participating and did not take the first place, obviously. So this is a proof point that IPUs can deliver very interesting performance characteristics for the graph neural networks. The 2 challenges that are included in OGBLSC were small graphs with molecule property prediction in this case, and the opposite of that, the very large knowledge graph where we had to predict missing links in the graph. And we have technical reports and implementations for these 2 cases published so that you can take a look and get some inspiration from that. A lot of effort is dedicated to enabling the ease of use and breadth of coverage on GNNs, and Fume is an example of that. It is a library that we are working on together with the team of Valence and Mila that enables experimentation for molecule-sized graphs. And let me try to present it in the repository. It's a public repository that anyone can use. And with a small set of steps to set it up, it enables featureization of the molecule graphs, and then graph neural network models of several kinds to be applied to those features that are produced in this repository, so that you can put together the building blocks and solve different prediction tasks at the molecule level in this case. But there are also node embeddings involved, of course, as well. So Graphium, we are inviting everyone to try and take a look and play around with it if you are interested in computational chemistry and modeling of molecule behavior with that. And overall, a lot of effort is going into supporting PyTorch geometric, which now is a preferred tool to build GNN models with. It offers a set of nice APIs to sample from larger graphs, create smaller graphs, put those graphs together in batches, and feed those to model architectures, defining building blocks for that as well. So Graphium will be a higher level construct, higher level library, with PyTorch geometric being the lower level set of APIs that, of course, run on PyTorch and etc. So in combination, altogether works very nice on IPUs. And as I said, this is because of the MIMD structure and the high memory bandwidth on the IPU. PyTorch we've covered yesterday. PyTorch geometric, we have released publicly support for that with the IPU, and we have a good coverage of the operations there. And it's easy to start using it. Now, a couple of...
There's a question before we get too far ahead of it. I'm not sure if it was related specifically to anything with Graphium, but it was what kind of neural network models do you support? I'm assuming referring to which GNN types. So I know there were, on Graphium, there were multiple GNN types that were listed there, and we do support each of those that Graphium is supporting. Beyond Graphium could support other types as well.
Yeah, so there are a set of, well, there is a set of examples of GNNs that you can easily access on this model garden page that we have. I just filtered by GNNs as a category here. So there is TGN, GIN, SNET, GCN, and other models. But overall, you can build any kind of architecture using the building blocks that we support and that PyTorch geometric provides. For example, GPS++ with some modifications is the model that we used to approach this OGB competition for molecules. So there is a spectrum that you can pick and choose from. Does this answer your question? Okay. Thank you. I'm happy to follow up later if you have any specific models in mind. So the environment that we have to work with on IPU, as I mentioned yesterday, is involving the ahead of time compilation. And that means that we need to know the shapes of tensors ahead of time. Is beneficial for us because we can structure the communications and memory allocations on the chip in a more optimal way. And for us, that means that we need to slightly change the structure of the program of the TensorFlow, tensor shapes that PyTorch geometric produces and uses. So on, well, a typical scenario when PyTorch geometric creates a mini batch would be as such. We have a number of small graphs, maybe molecules that we want to work with. And what PyTorch does, the data loader there, is creating mini batches of size 3, for example, and those will look like this with the numeration, the order in which we have those in the data set, and the sizes of those mini batches can be different. So I should mention that these squares represent adjacency matrices of the small graphs. So this is a structure that is not fixed in terms of its shape. And one way to do that is to use padding. So a way to achieve fixed sizes, and I should mention that PyTorch geometric does not use the dense representation of those adjacency matrices combined, but uses a sparse representation of that, but still the point stands. We can add a padding graph to each of those combined niches graphs. So it would look something like this, with all the batches having the same shape. And in the sparse representation, there will be a portion associated with the padding graph that we will have to account for when running the computation on the graph. Specifically, we will need to make sure that the loss is not being propagated, the portion that comes from this padding graph. Functionality is enabled by the fixed size data loader, where you define the number of nodes and edges that is involved. And we can go a little bit further than this, because you can see that if we fix the number of items, number of molecules that are used to put together in a graph, it can be, in some cases, wasteful, because the padding graph in this case is very large, and we could probably have used this space to fit a smaller graph into the same batch and not lose the computation that will anyway happen to this padding graph. So this can be done with a technique that we call packing. It was first introduced. Oh, sorry. I should mention that the padding graph, we chop it off the portion of the loss that comes from it when computing the loss before the back propagation is shown here, so that it does not change the actual gradients that we have. So this is another thing that we need to take care of when using padding. Now, switching to packing, this is a technique that allows us to put some larger number of subgraphs into the batch dynamically, so that the size of the padding graph is minimized. This technique was first introduced for natural language processing, actually, when training a model or running inference. In some cases, the attention, the tiny sequences with fixed shapes of tensors in the computational graph would mean large paddings. So putting together small sequences to minimize padding is helpful, and it helps increase the throughput when training a model or running inference, both in case of sequences of tokens and graphs, as shown here. The downside is that instead of 3 fixed number of graphs in a mini batch, you can have more, and you can compensate for it by computing maybe an average amount of graphs in a mini batch and modifying the learning rate accordingly. So the sparse representation, the batch variable vector in PyTorch geometric data loader will look something like this. And there is a paper describing this, so you can refer to that. With this, we achieve an optimal combination with fixed tensor shapes and small padding graphs combined. There can be some other dynamic constructs in PyTorch geometric, which we want to solve before the compilation happens. And self loops is one of those constructs. For example, the GC and conv layer has an argument that can dynamically add self loops to the graph when a node is connected to itself to propagate kind of the messages to itself. And instead of doing that in the forward pass, we can push it out of the training loop of the forward pass into the data pre-processing phase, where we add a transform to the data to add self loops automatically before the forward pass happens. And another dynamic aspect is masking of specific nodes for each batch. If, for example, we want to compute the loss for specific nodes only, And instead of instead of this dynamic operation, which has shape that changes from one batch to another, we can use this torch where and replace the values in the output tensor based on the mask with minus hundreds, which is treated by the loss function as a value that you need to exclude from the computation. And in this case, we have the static shape for the tensors, so it runs well. With PyTorch, the software stack looks like this. This is like a different view on that compared to the one I've shown yesterday. So there is PyTorch. PyTorch geometric will be on top of PyTorch here. Then we have PopTorch, PopArt, and the software stack with the libraries and drivers that run on hardware. And the changes to the code were described yesterday. It's the training model and inference model wrappers around the PyTorch model objects, and the changes to PyTorch geometric operations described on the previous slides. In terms of our support for PyTorch geometric, there is this ecosystem of things that exist within PyTorch geometric, from models to data loaders to different operations that PyTorch geometric enables. And it runs on PyTorch, making a heavy use of gather and scatter operations and sparse operations there. What we have done, we have ensured that most of the layers are supported from PyTorch geometric on the IPU. We have created data loaders that produce batches of fixed size, fixed shapes, and enable packing, including packing on the fly or stream packing. And we have provided fast optimal implementations of operations that are important for PyTorch geometric, such as gather and scatter operations that are used in the message passing mechanism in the models. A couple of words about the message passing and why gather scatter are important here. When we aggregate the embeddings with from the neighboring nodes to compute a new embedding, aggregated embedding for a specific node in the graph. An operation like this happens. So first of all, from all the embeddings that we have stored in a tensor for a given, we need to pull only the neighboring nodes, and that's a gather operation that's happening. And then after that, we need to put those through a transform and store the result for this node in the updated, well, update the embedding for this node that we are working with. And that is a scatter add operation, updating the embedding of the node based on the messages that come from the neighboring nodes, given their embeddings and the embeddings of the edges that connect the nodes in this neighborhood. So this operation is a set of, or can be represented as a set of gather and scatter add operations. In our experiments, we have benchmarked the scatter add operation and the gather operation on the IPU compared to the GPU, A100 in this case, for different sizes of inputs and outputs of the operation, finding that while for very, very large numbers of output sizes of inputs and outputs, the performance is on par. For smaller combinations, IPUs outperform A100s by a large number, over 16x in case of scatter-add, and then over 8 times for the gather operation. So given this fact and the fact that gather and scatter are so important for message passing, and that is in its turn so important for GNNs, IPUs are showing a very good performance on GNNs. That has enabled us to make more experiments for the OGB challenge, for example. And again, this is because of the different architecture that we have on the IPU, high memory bandwidth, fine-grained communications. For the SCHNET implementation as a case study of that, this is a public example that you can run. For example, you can do it either in the on the pod 64 that ANL has, or an alternative is to run it in Paperspace in the cloud, which has a notebook that you can walk through to reproduce this experiment. The notebook describes the statement of a problem and the architecture of the model. In this case, we are trying to analyze molecules represented as graphs based on the distance between the atoms in the molecule, based on the positions, 3D positions of the atoms in the molecule. And we say that in this model, in case of SCHNET, we say that atoms that are close enough to each other have an edge between them in the graph. And we predict the graph level property, homo-lumo gap in this case, which is a very popular target for prediction. It's a regression graph level task in this case. So the steps that are taken to implement the SCHNET model on IPUs are exactly as I described earlier. So from the data loader that produces batches of varying shapes, we can use either padding, or we can use packing on the fly and make sure the shapes are kept the same. In this case, we want batch size 8, and we fix the size of the combined batch to this number of nodes using the custom fixed size data loader from the IPU implementation of the PyTorch geometric. And based on that, we have the shapes of the tensor for different batches that are the same from batch to batch. And then we implement a few optimizations to the model. For example, the ones that I've mentioned yesterday, we use a higher number of device iterations. So there is a loop on the device that processes several batches in one run. We use gradient accumulation that, by the way, conserves the overall global batch size if you replicate across more than one IPU. And we, use executable caching so that the graph is not compiled every time we run it. And then the replication factor, the number of IPUs the graph runs on, is defined here in this line. So that's it. With this, we can use PopTorch Atom Optimizer, which again is an optimal, slightly optimized implementation of the standard, similar in the behavior though. And we can show that the model is training and the loss is going down nicely. So with this, we were able to achieve state-of-the-art accuracy on the model, faster. And this slide shows, again, similar to the model garden, a number of examples and models that we have implemented. So I have 15 minutes left. Happy to answer any questions. Please feel free to step in and turn on your microphone or message in the chat. And we'll have also some time for questions and answers later today. I will try to very quickly run through the large language model portion. The NLP models are, well, the most popular library for those is Hugging Face. And Hugging Face have collaborated with GraphCore, producing this optimum GraphCore set of scripts library as well, which allows one to run a large set of models using Hugging Face APIs on the IPUs. The documentation that the website shows is pretty extensive, and the changes to the code that one would need to make when switching from GPU to IPU are shown in the README file on in the Optimum GraphCore library. I will walk through those changes now. You basically need to use the Optimum Graph Pipeline class and instantiate with that using another argument. Let me try to actually open that now, the Optimum GraphCore part here. I just show that there is another argument, the IPU config, that is also stored in the Hugging Face repository for GraphCore. And then the other changes are